Good morning. It's a pleasure having you all here today. Thank you for coming. This is a very important subject to Brazil, not only for Brazil, but all countries are interested in this subject. So Brazil is putting, the Brazilian government is putting a lot of emphasis on this subject, and the reasons you all know. And as you also know, we have a methodology that we will follow, similar to the other days. We have two presentations, and we will start with a friend of mine, a colleague from Petrobras. Dennis Miller will present on gas hydrates. And following the structure that we already have during the seminar, the questions will be made at the end of the second presentation. So let us see the presentation, see the second presentation, and at the end of that, we'll have some time to make some questions, to make some comments before we go to the coffee break. Thank you. Dennis, please.
Good morning. My name is Dennis Miller. I'm a geologist. I work for Petrobras at the R&D Center here at Rio de Janeiro. Today I will present to you gas hydrates in the Brazilian continental margin, inferred occurrences, and current investigations. My presentation will be, the outline is first a definition of what gas hydrates are, characteristics of the gas hydrates, associated features and seismic records, mainly BSRs, potential as energy source, inferred occurrences in Brazil, and I have put a couple of slides from Africa as well, current investigations in Brazil, and conclusions. Well, gas hydrates, what are gas hydrates? They're compounds occurring in nature as crystalline solids in the form of ice, where gas molecules that act as guests are trapped by a lattice of water molecules that act as hosts, forming cage-like structures known as clathrates. So these are the clathrate structures here, cage-like water molecules form a cage-like structure, and in the center we have the gas molecules, which are gas molecules. So this structure is called a clathrate, and gas hydrates are a type of clathrate. So a lot of people use clathrates and gas hydrates as synonyms, but they're not necessarily synonyms. Hydrates are a type of clathrate. Common examples are methane hydrates and CO2 hydrates. So in those cases, the molecules inside the cages are methane and CO2, but we can have other gases as well inside the structure. They're found in nature below the permafrost and polar regions, as you can see on the map here. The polar regions here in the northern pole, and mainly in Siberia and Canada, and perhaps there should be a lot also in the Antarctic. And in marine or lacustrine sediments in water depths generally exceeding 400 to 500 meters. The gas hydrates occur in three different chemical structures: structure 1, structure 2, and structure H. This is a general scheme of the chemical structures of all three of them. And this is a diagram from Sloan, where we have a single cage with a molecule inside, and structure 1 has two different cages and forms this crystal structure. Structure 2 has two different cages also, but the second cage is larger than in the case of structure 1, so it can have propane as a gas, isobutane, natural gas, whereas structure 1 can have methane, ethane, or carbon dioxide. And we also have structure H that has three different cages, and the third one is large enough to have two gas molecules, sometimes methane and neohexane. Going on to the characteristics, conditions for formation. This is important, we all understand this. Gas hydrates, they require specific conditions for their formation. And those conditions are high pressure, low temperature, high gas concentration. This is very important because a lot of people don't put emphasis on a high gas concentration. You have to have gas to have gas hydrates. Here we have a phase diagram, a phase stability diagram, and a hypothetical case of seafloor at 1,200 meters in water depth. So this is the diagram we have on the y-axis, the depth, which it's equivalent to the pressure, and the temperature on the x-axis. We have the seafloor at 1,200 meters. The yellow part of the graph is a hydrate stability zone. This curve is a gradient of the temperature of the seafloor, and this is the geothermal gradient. So when the temperature of the seawater reaches around 450 meters, you have conditions of forming gas hydrates if you have sufficient gas concentration. In this case, when the seafloor is 1,200 meters and you have gas concentration, you have a gas hydrate stability zone, which will be, the thickness will depend on the geothermal gradient. The higher the geothermal gradient, the shallower it will be. And the lower the geothermal gradient, the thicker it will be, the deeper it will be. So the gas hydrate will dissociate from the water once these conditions are not met. When the temperatures exceed, in this case, between 10 and 20 degrees, or when you release pressure. So in this case, you have probably a dissociation by both pressure release and temperature, and here the gas is dissociating and burning. Characteristics, different morphologies. They have found different morphologies in gas hydrates. Some examples are shown here. First one is filling oblique and subvertical fractures in muddy sediments, and this is quite common. You see here, this is a tomography image, and the white fractures here are filled with gas hydrates. The length of the core is 90 centimeters, and here we have some sections. Over here you can see how complex the fracture pattern is. Another form of occurrence, another morphology would be nodules, lenses, layers or laminations in muddy sediments, or disseminated in sands. And these are the type of deposits that today are being tested. Types of deposits. Walsh classifies gas hydrates deposits into 4 types. Type 1, hydrate deposits over free gas zones. Type 2, hydrate deposits over water zones. Type 3, hydrate deposits over no mobile fluids that would be inside the gas hydrate stability zone at isolated lenses. And type 4, localized and dispersed deposits on the seafloor, which are quite common in places like in the Gulf of Mexico. Only types 1 and 2 are exploitable with the current technology. So current technology cannot extract gas hydrates from these type 3 and type 4. Potential uses of gas hydrates: as an energy source, as gas storage and transport, geologic storage of CO2, where the idea is to inject CO2 into the reservoir, and the CO2 will substitute the methane molecule, and you'll keep your hydrate in the formation and you will produce methane. This is the idea. It's being already done experimentally in laboratory. Another use is hydrogen storage, seawater desalinization, and refrigerating systems. Associated feature in seismic records. The occurrence of gas hydrates are generally associated to specific features in seismic sections. And that's how we identify the possibility of having gas hydrates in geologic settings. BSRs, which are bottom simulating reflectors, are considered the most diagnostic. And I'll explain to you why they form, why they show in seismic records. This is a diagram from Clennell in 2000. We have different curves here. This is the hydrate stability curve. This is the gradient, the temperature gradient on the seafloor and on the soil, the sediment. And this is the seismic velocity. Okay, we have a constant seismic velocity which enters the seafloor and increases. The seismic velocity increases due to density increase. And then when it reaches the bottom of the hydrate stability zone with a free gas zone in the bottom, the velocity just decreases abruptly. And we have a decrease in density as well. So what that turns out to be a difference in acoustic impedance, which causes the BSR to form. As you can see here, the grains are surrounded by water and hydrate, and in the free gas zone is gas and water. So you have a density and a velocity contrast. And that's why we get a reflector here called BSR simulating the seafloor. Other related features are gas chimneys, acoustic blanking and turbidity, high amplitude reflectors, mounds, elevations on the seafloor, pockmarks, which are depressions on the seafloor, and acoustic plumes, which are plumes inside the water column. Here's an example of a seismic section from the Canadian continental margin displaying a BSR. It would be this reflector mimicking the seafloor. Some comments regarding the BSRs as a diagnostic tool for gas hydrates. Gas hydrates are not always present when BSRs are observed in seismic records. So in some cases where you drill where the BSR is, you don't find gas hydrates. Another possibility, gas hydrates can be present where BSRs are weak or absent. So in this case where it's, the BSR is absent or weak, sometimes you do find gas hydrates in those places. Barrett and colleagues have shown that similar BSR features, or features that look like these BSRs, can also occur where diagenic transformations from OPO-C to OPO-AT and from smectite to illite have taken place, and where large amounts of orthogenic carbonate have been deposited. So BSRs can be something else than gas hydrates. So a potential energy source, according to Sloan, the great energy potential of gas hydrate derives from the fact that one volume of gas hydrates with total occupancy of gas cavities corresponds to 180 volumes of gas at surface. So you multiply your volumes that you have in the gas hydrate by 180, and that's how much you would have at surface. Some authors estimate that gas hydrates may contain more than twice the amount of energy than all other fossil fuels combined. That's what these authors say. However, recent estimates indicate varying recoverable volumes depending on the type of reservoir and the geologic setting where it occurs. And this is where these pyramids come in by Boswell and Collett. And this would be the total volume estimated of gas hydrate and all other gas resources. The three upper layers here in this pyramid, which is developing or proven reserves of all other gas resources, would probably be equivalent to these first three layers here, which are Arctic sandstones under existing infrastructure, or Arctic sandstones away from infrastructure, or deep water sandstones. So this volume probably corresponds to this volume, and this is what we can probably extract nowadays with the technology available. So with the technology, we probably have something, we would double the amount of gas that we'd have available today as far as the resource is concerned. So I don't know if it would be the double of all fossil fuels. It would be 1 times more what we have here as a gas and other resources. Production from permafrost, production tests carried out in Malik 2L38 and Malik 5L38 wells in northwest Canada. This was done by a consortium between Canadians, Japanese, Americans, I believe Germans also. They performed a test on these 2 wells, and the test was done using depressurization. This is a well test assembly. The reservoir would be around here, around 30 meters in thickness. What they did, they placed a pump here where the reservoir was, and they pumped the water out of the well, so they took out the pressure, the hydrostatic pressure from the well. And that meant that the hydrates dissociated and were produced. The test, there were 2 tests, and one in 2007 that produced 130 cubic meters in 15 hours. And the test in 2008 was 140 cubic meters in nearly 6 days. So this is not a very significant production when compared to conventional gas wells. Okay. Production from deep water sands, the ones that are the country that's probably the closest to producing deep water sands is Japan. The production tests are expected within the next 5 years in deep water turbidite sands and the Nankai Trough, east of Japan. The in-place gas volumes are estimated to be 20 TCFs. They have already drilled, I believe, about 12 or 13 wells in the Nankai Trough, so they have a very good control of where the hydrates are and how they occur. So this is a pretty good estimate, 20 TCFs for that specific deposit. So what are the challenges? The challenges, first, is a slow dissociation, relatively low production. So in the hydrocarbon industry, we're used to producing fluids in the reservoir, either in the gas or the liquid state. Gas hydrates are in the solid state in the reservoir, so you have to dissociate them. And they dissociate rather slowly. Most significant water and sand or mud production from relatively unconsolidated reservoirs. As you produce, there's a lot of sand being produced and mud, so you have to take care of that. Either displace it or inject it in another well. Another fact is the horizontal dissociation front. Horizontal wells are not as effective. In normal hydrocarbon reservoirs, hydrocarbon wells are very effective to increase production. Some authors claim that in gas hydrates, the dissociation front is horizontal. It doesn't go vertically. So it doesn't make much of a difference if you're producing from a horizontal well or a vertical well, according to some authors. Secondary hydrate formation in the well and production lines, the hydrate may form again once it's dissociated. It might form again, it might crystallize again inside the well or in the production lines. Well instability, we're producing from a reservoir, a rather inconsolidated reservoir, and we're producing part of the reservoir as well, so you can have a well instability. And overburden collapse. You're also taking some part of the reservoir, the overburden might collapse. So these are the inferred occurrences in Brazil that we know until now. The first one I'm going to mention is the Rio Grande cone, which is down the southern tip of Brazil. And the Pelotas Basin, the estimated area is 45,000 square kilometers within the bathymetries from 500 through 3,500 meters, and an estimated volume of 780 TCFs. If you remember correctly, the Nankai Trough is 20, so this might be a little bit overestimated. Some seismic lines showing some features. This is the BSR, okay, following the seafloor, and the upper to middle continental slope and the Rio Grande cone. As you can see here, there's a lot of what we call gas chimneys that may be actually faults that are reaching all the way to the seafloor and running through the BSR. Another section here going down to the mid or lower continental slope. It's a very noticeable BSR. You see that in the seismic record we have a frequency change from above and below the BSR, a lower frequency below the BSR, and amplitudes are a little bit greater also below the BSR. Now another seismic section on the continental rise below the thrust and fold belt. We see the BSR following the seafloor as well, and this is in water depths of around 3,000 meters. So we do have BSRs in deeper portions of the basin as well. Now I'll mention the Amazon cone occurrence. At the Foz Amazona Basin, the area is 28,000 square kilometers, bathymetries from 600 to 2,800. Estimated volume 430 TCFs. This is being remapped by some groups here in Brazil, and it seems like the area is a little bit larger than this. But this volume, again, it may be overestimated. Seismic records from the Amazon cone. This is on the thrust and fold belt, and we can see a reflector cutting all the normal stratification. This is the BSR where we suspect there might be gas hydrates. Another section from the thrust and fold belt. This reflector right here is interpreted as a BSR. Another cross-section on the thrust and fold belt, a very straight BSR following the seafloor. And other BSRs along the Brazilian continental margin that we have in other basins, a little deeper. This is around probably 500 to 600 meters, and another quite clear one down here. Well, other areas in the Brazilian continental margin to be investigated for gas hydrate accumulations. This would be the model that we could follow to investigate gas hydrates in these settings. These are deltas, prograding deltas on the coast, the continental shelf, the slope, and the rise. And these deltas, they may prograde into canyons that feed into a fan or cone. And exactly in these fan or cones, just like in the Amazon cone, that's where we could look for gas hydrates if we're looking for biogenic gas hydrates. If we're looking for thermogenic gas hydrates, anywhere you have a reservoir with hydrocarbons, you might have gas hydrates over them as well. This is the Parnaíba River Delta in northeast Brazil, San Francisco River Delta in northeast as well, Jequitinhonha River Delta, also in northeast, and the Doce River in the state of Espírito Santo in the southeast margin of Brazil. Well, I have placed also some occurrences in Africa from Cunningham. This is a BSR isopac map in the Niger Delta. This is the isopac, the thickness of the BSR as mapped by Cunningham. And we see there's quite substantial areas here in the Niger Delta as well. This is a seismic section showing the BSR. Not as clear as the other sections that I showed, but this is interpreted as BSR in the Niger Delta. Occurrences in other places in Africa, the Congo Slope, a big canyon here at the coast of Congo, Cabinda, and Democratic Republic of